Welcome to AP Chemistry. I'm Jim Burnham. Today we're going to be talking about the first unit of the 9 units of AP Chem. This covers atomic structure and properties, and it's usually between 7 to 9% of the AP exam in terms of its content. First topic is moles and molar mass. The mole is probably the single most important concept in chemistry because it allows us to convert from atomic mass units in the periodic table to actual grams of something usable in the lab. So we use the mole to compare and convert to different other units. We can go from mass in grams to moles, and then from there to number of particles, and if we're dealing with a gas, we can even convert to volume. So we often talk about mole island. We're going to go through mole island. So if you start over here with the number of particles, if you have an Avogadro's number of them, which is 6.02 times 10 to the 23rd, you can convert them from the number of particles to the number of moles. And then once you're here, you can go to the number of grams, because you multiply your moles by the molar mass to get to gram island, or you divide by the molar mass to get back to moles. And if it's a gas, you can multiply. So let's say you have 1 mole of something. We know that it's 22.4 liters per mole, so you have 22.4 liters of a gas. Or let's say you have 44.8 liters of a gas. You divide that by the number of liters per mole, and you find out we have 2 moles. So the mole is kind of, we call it the chemist's dozen. It's the unit that allows us to convert between number of particles, weight, and volume if it's a gas. So the mole allows us to calculate quantities of a substance or its number of particles. Atoms and molecules are inconceivably tiny. They are way too small to count directly. They're way too small to even see, even with the most powerful microscopes. So we count them by weighing. So we can weigh, we can get the number of particles by weight. If you had to guess how many molecules of water would you think are in 18 grams of water, which is just over an ounce? It's not millions or billions or trillions or even quadrillions or quintillions. It's 602 hextillion molecules, which looks like this. It's a massive number. It's an astonishingly large number. Hundreds, thousands, millions, billions, trillions, quadrillions, quintillions, hextillions. That is what Avogadro's number represents, 6.02 times 10 to the 23. We call that number a mole. Not this cute guy, by the way. That's just a nice picture. The average mass of an atom or a molecule in atomic mass units equals the molar mass in grams. So the mole, bottom line, allows us to take the atomic mass, the average mass in atomic mass units, and that's what we find. We find that on the periodic table. We can take that and we can go to the mass of a mole of that in grams. So an Avogadro's number of any element, say carbon 12, gives us 12 grams of carbon. Yeah, we go from the 12 atomic mass units of carbon 12. If we have an Avogadro's number, 602 hextillion of them, then all of a sudden we will have 12 grams of carbon. So this is a useful conversion. The number of moles, N, equals the mass divided by the molar mass. All right, that takes us to our second topic, mass spectroscopy of elements. And this will help us explain the quantitative relationship between the mass spectrum of an element and the masses of its isotopes. So spectroscopy is, we studied the interaction of electromagnetic radiation with matter. So we can bombard a sample of matter here with electromagnetic radiation, and it will absorb some of that radiation and then give off a spectrum, which we can read on our spectrometer. So the mass spectrum of a sample containing a single element can let us identify the isotopes of that particular element and their relative abundance. Remember, an isotope is the same element, so it has the same number of protons. Remember, it's the protons that determine the identity of an element. So an isotope, it has the same protons as any other atom of that element, but it might have a different number of neutrons, in which case it will have a different mass. And that's what isotopes are. They are variations of an element based on their different weights. And we can tell the weight and the relative abundance of the isotopes using a mass spectrum. So here, for example, is a spectrum readout of magnesium. And what we see here, on the left side, we're going to see relative abundance, usually on a scale of 0 to 100%. And down here, we're going to have our mass to charge ratio. And basically, that lets us know how heavy each of these things are that's hitting our spectrometer. And in this case, we can see that the mass, the atomic mass of these things that weigh 24, it's 79% magnesium 24, and 10% magnesium 25, and 11% magnesium 26. So this tells us that both the number of the isotopes of magnesium, in this case there's 3 isotopes, and it tells us the relative abundance of those isotopes. It says that most of magnesium is magnesium 24, almost 80%, and the other, roughly 10% each, is magnesium 25 and magnesium 26. So we can estimate the average atomic mass of an element from the weighted average of the isotope masses. So if we know, for example, that here's our spectrum of chlorine, about 75% of chlorine is chlorine 35, and 25% or so is chlorine 37, we can find the weighted average. We can say, well, listen, I'm going to multiply 35 AMUs times 75%, and then I'm going to add 24.24% of chlorine 37. And when I add those together, it will give me a weighted average of the isotope. All right, our third topic is elemental composition of pure substances. And so this allows us to explore the quantitative relationship between elemental composition by mass. So we can find, what percentage of some compound is of various elements. And we can look at the masses of each of those individual elements. And from that, we can determine the empirical formula of that compound. Now remember, chemical formulas identify substances by their unique combination of atoms. So here's calcium carbonate, also known as chalk. Right? It's made up of 3 different elements. It's a compound of 3 different elements. It has 1 atom of calcium, 1 atom of carbon, and 3 atoms of oxygen. And all calcium carbonate will have that same composition. Some pure substances are composed of individual molecules, like water, so covalent compounds are made up of individual molecules, while others consist of atoms or ions held together in fixed proportions, described by a formula unit. For example, the ionic compound sodium chloride or table salt. And we describe that as NaCl, but it doesn't exist as one Na and one Cl. It exists as a whole complex, a crystalline lattice network of sodium and chlorines. But they are in a 1-to-1 ratio. And so we describe it like this. But this is not describing an individual molecule. It's describing the proportions of each of the ions that make up that ionic compound. So according to the law of definite proportions, the ratio of masses of the element in any pure sample is always the same. So if we find out, for example, that the proportion of oxygen to hydrogen in water is, say, 88%, somewhere close to that, then it's always going to be 88% if it's water. And it doesn't matter where the water comes from. If it's water from Russia, if it's water from India, if it's water from Brazil, it's going to have the same ratio, the same proportion of oxygen to hydrogen, 88% or whatever that is. So the chemical formula that lists the lowest whole number ratio of atoms in a compound is known as the empirical formula. So for example, we know that the molecular formula of peroxide is H2O2, but the empirical formula would be the lowest whole number ratio, in which case we could divide both of these by 2, right? And we would get HO. So HO would be the empirical formula. That's the ratio of the elements to each other in this molecule. But that's not necessarily the molecular formula. Right? So there can be a difference between the empirical formula and the molecular formula. Sometimes the empirical formula is the molecular formula, but not always. So here are some examples of differences between empirical and molecular formulas. So the empirical formula is the simplest whole ratio, the simplest whole number ratio of elements. CO2, that happens also to be the molecular formula. H2O, the empirical formula, also happens to be the molecular formula. But NO2 actually exists in N2O4. This is the empirical formula, P2O5, but it really exists as double that, as P4O10. Lowest whole number, C5H22, but actual, in reality, C10H22. C2H6O, but in reality, it exists as a triplet. And what you'll always notice is that the molecular formula is always some whole number ratio, whole number multiple of the empirical formula, either multiplied by 1, by 2, in this case by 3, or some other whole number. Composition of mixtures. So now we look at the quantitative relationship between the elemental composition by mass and the composition of substances in a mixture. And remember, we already said chemical formulas identify substances by their unique combination of atoms. Pure substances, by definition, contain molecules or formula units of a single type. They're not adulterated or diluted or contaminated with anything else. So here, if we're dealing with, say, sodium chloride, NaCl, if it's a pure substance, then the only thing in that sample will be sodium chloride. If we have sand in there, if we have sugar in there, if we have some other compound in there, then it is no longer a pure substance, it becomes a mixture. Mixtures contain molecules or formula units of 2 or more types whose relative proportions to each other can vary. So for example, if I take a pure sample of sodium chloride and I mixed it with some sugar, right, then I'm going to get a proportion of sugar to salt. But if I keep adding sugar, that's going to change the relative proportion of the sugar to the salt. I mean, I might start out with 10% sugar and 90% salt, and then I might get to 50-50, and then I might get 90% sugar and only 10% salt. So the proportions in mixtures can vary. Elemental analysis can determine the relative numbers of atoms in a substance, and thus its purity. So we can see that the closer it approaches the purity of a pure substance, right, we can tell how impure a substance is. Okay, the fifth topic is atomic structure and electronic configuration. And this is really one of the core concepts that helps us decode and read the periodic table, and it helps us appreciate the various trends of properties associated with the periodic table. And the reason the periodic table is periodic, that is because we have repeating similarities of electron structure. So we're going to represent the electronic configuration of an element or its ions. Remember, ions are simply that element with either gaining electrons, so it becomes a negatively charged ion, or losing electrons and thus becoming a positively charged ion, also known as a cation. So we're going to represent this using what is known as the Aufbau principle. And the Aufbau principle is going to be a way that we build things up from their lowest energy state to their highest, one electron at a time. So when we look at this, we know we can identify atoms and molecules by their electron distribution and energy. Now, quick review, we should know this already from general chemistry. The atom is composed of negatively charged electrons in an orbital cloud surrounding a positively charged nucleus. And the nucleus is very, very small in proportion to the whole size of the atom. And the nucleus is made up of positively charged protons and neutrally charged or non-charged neutrons. So here is the Bohr model of a nitrogen atom. And in this case, we have, what do we have? 1, 2, 3, 4, 5, 6, 7 protons, and maybe an equal number of neutrons. Could be, looks like there might be. And then that's the dense core known as the nucleus. And it's surrounded by these concentric shells of orbital clouds. Now it's hard to depict an entire orbital sphere, kind of a fuzzy sphere, so we depict it like it's in a planetary orbit. We know that's not true, but it helps us to keep track of things and to see the various shells and the various energy levels of the electrons in those shells. So in atoms and ions, the electrons can be thought of as being in shells, which we would call these, this would be shell number 1. We see 2 electrons in shell number 1. And then in this case, 5 electrons in the second shell. So when you hear the word shell, think energy level. And when you hear the word subshell, think sublevels within that particular energy level. The first energy level is known as, or shell is known as the 1. And there are there's one subshell known as the S subshell, and it can hold up to 2 electrons. Then we go to the second shell, which has an S subshell and a P subshell. And the S holds 2 and the P can hold up to 6. So there's a total of 2 electrons that can be held in the first shell, and a total of 2 plus 6, or 8 electrons that we can hold in the second shell. What of the third shell? Well, there's 3 subshells. There's an S, a P, and a D subshell. This can hold 2, this can hold 6, this can hold 10. So the third shell can hold a total of 18 electrons. 2, 8, 18, and the number keeps coming up. So there's this diagram that will help us fill these correctly. So if we think about going kind of diagonally here, we're going to fill the 1 S's, so they're full. Then we start with the 2 S's, so they get full. Then we go to the 2 P's, so they get full. Then the 3 S's, and then the 3 P's. And we're not going to go to the 3 D's just yet. We're going to go to the 4 S's, then the 3 D's, 4 P's, then the 5 S's, then the 4 D, 5 P, and so on. So this is a great chart to get the predicted filling order, the predicted Aufbau, lowest to highest filling order. And we write this out like this. So here's how we would depict carbon. Carbon has, it's got 6 protons, therefore 6 electrons. In a neutral atom, the electrons always balance the protons. And so it's got, we would say this is 1s2. Those are the 2 electrons in the 1 shell. 2s2, that's the 2 electrons in the 2s subshell, and 2p2, 2 more electrons in the 2p subshell. So this would be the exact electronic configuration for carbon, and no other atom will have this configuration except carbon. Well, I guess that's not true. You could have something that's isoelectronically identical to this. Some other cation or anion that might have its that might be isoelectronically the same as this. But this is how we identify the electron configuration of something with 6 electrons. Okay, we distinguish between inner electrons and valence electrons. The inner electrons, the ones closest to the nucleus, are known as core electrons. So here in carbon, remember back, we see that this one shell is closest to the nucleus. These are the core electrons, and these 4 other electrons in the 2 shell are known as the valence electrons. And the valence electrons are where all of the magic happens. The physical and chemical characteristics of all elements are determined almost entirely by the valence electrons. They are the ones that that are either added to or taken away from. If we add to them, we get negative ions. If we take them away, we get positive ions. But the combination of those ions and cations, and we can form covalent bonds with other atoms to get complete octets and all that kind of stuff. All of that happens because of the valence electrons. So electron configuration is explained by quantum mechanics, which happily we don't get into at any depth. We certainly don't get into any mathematical descriptions of quantum mechanics, happily. But and it's delineated in the Aufbau principle and exemplified in the periodic table. So electronic configuration it's what makes elements the way that they are and makes them work the way that they do, and it allows us to classify them in these repeating patterns in the periodic table. So the Aufbau principle is used to determine the electronic configuration of an atom or ion. According to the Aufbau principle, electrons will fill lower energy orbitals first. So we'll start here, we'll put one electron here, and then another electron here. They'll have opposite spins, as we'll see, because of the Pauli principle. Then we're going to put another electron here and another electron here. And after we filled the 2s, so 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, and we come back, 2p4, 2p5, 2p6. We don't double these up until we have to. We don't pair them up until we have to. That's known as Hund's rule. We'll cover all that in just a second. So we often use these kinds of charts to fill up the periodic table. And we can basically build every element in the periodic table one electron at a time. We add a proton, we add an electron, we get a new element. We add a proton, we add another electron, we get a new element. So by keeping track of the electronic configuration, we can determine the electron configuration of any particular element or any particular ion that also has that same electronic configuration. So here are our orbital filling rules. We said the Aufbau principle says fill the lowest energy orbitals first. So fill the 1s's before you go to the 2s's, and the 2s's before you go to the 2p's, and the 3s's before you go to the 3p's, and so on. Now the Pauli exclusion principle, as I alluded to, says orbitals hold a maximum of 2 electrons, and if you get 2 electrons in one orbital, they have to have opposite spin. They can't both spin up or down. We flip them, because that's the only way we can distinguish one electron from another when they're both in the same orbital. And we have to be able to identify every electron with its own specificity. It's just like we want to be able to define every seat in a stadium. So we might say, okay, well, this is section A, row B, seat 15. Right? And that's what we're doing here with the Pauli exclusion principle. Because two electrons, let's say we're talking about the 2s. If they're both in the 2s1, it's 2s1 and 2s2. They are both within the same orbital. And so there's no other way to distinguish one from another except by saying one must be spinning up and one must be spinning down. If it doesn't make sense, don't worry, just remember that's what you got to do. Hund's rule says you fill equal energy orbitals one at a time until each is occupied by one electron. Electrons in singly occupied orbitals have the same spin. So if we go back here, for example, we start filling this up, 2p is going to be, we're going to put one electron pointing up. And then we're going to point at 2p2, another electron over here in a different orbital pointing up. 2p3, one electron here pointing up. They're all going to be pointing up. Then if I come back here in 2p4, then this one will be pointing down. And now this is the first time I've paired up an orbital. So there'll be two here, and yet still one here and one here. And if it's 2p5, that fifth one will be here pointing down. 2p6, the sixth one will be here pointing down. So that is Hund's rule. We fill them one at a time until each is occupied by one electron. So we're going to look at various Aufbau principle rules, and we're going to see which ones are right. So if we just have a single electron and it's pointing one way, that's fine. If we have three electrons in say, the P's, then we're going to go 1, 1, and 1. That's good. We're never going to draw this. We're never going to draw two electrons pointing in the same direction. Why? That violates the Pauli exclusion principle. We can't distinguish these two electrons from one another unless one has an opposite spin from the other. So if we have to add this, this is how we would do it. If we were starting here and we added a fourth one, then the fourth one would be here in this first orbital, but with opposite spin. Again, we have to double up. We go single, 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 but when the fourth one comes along, we have to start doubling up. We're never going to have 3 in a suborbital because the max is 2. And you're never going to double up, according to Hund's rule, right, if you have an open urinal that's further away. So you're never going to double up until everything has a single. And only then will you double. Now there's something called Coulomb's law that is used to calculate the force between two charged particles. And Coulomb's law and something known as Coulombic attraction is a really critical concept in AP Chem. You're going to hear the term Coulomb's law and Coulombic attraction and Coulombic forces a lot. So you just have to get comfortable with that idea. And really it's just a fancy way of saying that the closer two charges are, the stronger the force between them. So just imagine a positive end of a magnet and a negative end of a magnet. If they're far apart, there's going to be very minimal force attracting them together. But as you get closer and closer and closer, they're going to begin to pull on each other more and more and more. And finally, if you get really, really close, the force becomes all the stronger. So the force is going to be directly proportional to the distance. So the closer that charge becomes, the stronger the force between them. This is also true if the force is between two positives. So flip one end of the magnet around. So now you've got the positive, say, the positive and the positive side of the magnet, or the negative and negative. And the closer you push them together, right, the stronger the repelling force is going to be. So it doesn't matter what the charge is, right, whether it's a positive, negative, attractive charge, or a positive, positive repelling charge, or a negative, negative repelling charge. The closer those things are, the stronger the charge, whether it's attraction or repulsion. So Coulomb's law basically states that the force of attraction or repulsion between two charges is directly proportional to the product of charges and inversely proportional to the square of the distance between them. So we measure the distance between them by going from calculated nucleus of each. And that gives us this R distance. And here we have a positive, a negative and a positive. The force is going to be pulling them together. Here we have a negative and a negative. The force is going to be pushing them apart. But whether it's an attractive force or repulsive force, it's going to be the product of this charge. So if this is a +1 and a -1, that's going to be one charge. But if this is a -2 and a -2, this charge will be -2 to -2. This will be 4 times stronger than this charge. So the repulsive force of a -2, -2 will be 4 times the strength if they're the same distance apart of a -1 and a +1. So this is the way we represent this. We say the force is directly proportional to the product of the forces and inversely proportional to the square of the distance. And so we can put those together. So this makes sense, right? The stronger the charges, then the stronger the charges of attraction or repulsion. And since this is a denominator, the bigger this distance is, the lower the force. But the smaller this number is, then the higher the force. If I make the denominator big, then the fraction grows and the number gets smaller. So that's a very simple mathematical relationship. We put them both together here, and so this becomes Coulomb's law. The force is proportional to the product of the charges and divided by the square of the distance. So the bottom line, as you can see, when you look at this, as charge increases, right, as charge goes up, as we get a higher Q times Q, Q1 times Q2, then the force is going to go up. As the distance decreases, then the force will go up. As bond length decreases, so the bond length between two things, that's going to decrease the distance. Then the force will likewise go up. So decreasing bond length is the same as decreasing distance. So Coulomb's law can help us estimate the relative energy required to remove an electron from a subshell of an atom or an ion, something that is known as ionization energy. It takes energy to pull a negatively charged electron away from the positively charged nucleus. And the amount of energy is going to vary depending on how far away that negative charge is to the positive nucleus. The closer it is in those core subshells, the more energy it will take to ionize and to release that electron. The further it is away from the nucleus, the less energy it will take to ionize or take it away from the nucleus. So ionization energy is related to the distance from the nucleus and the effective charge of the nucleus. And the charge is going to depend on the number of protons. More protons, more effective charge. Again, depending on shielding. And so this is why, for example, when you look at atom size, it's why it decreases as you move left to right across a row. So if you take sodium here, this is pretty big, and calcium, and boron, and carbon, and it just gets smaller and smaller and smaller as you go. Why? Well, because we're adding more and more protons to the nucleus. And even though we're adding extra electrons every time we add a proton every time we add an electron every time we add a proton. But those are not any further away. They're in the same shell. And since they're not any further away, the more protons we add, the tighter those electrons get pulled toward the nucleus. And thus, the more ionization energy it takes to release them. So we're going to see decreasing radius, increasing ionization energy, and other various trends associated with Coulombic attraction between the electrons and the protons. Okay, this takes us to something called photoelectron spectroscopy. Say that 3 times fast. We're going to look at the relationship between a PES spectrum, that is a photoelectron spectrum of an atom, and we're going to look at the spectrum that it makes and relate that to the electronic configuration of the species. And we'll also explain the interaction between the electrons and the nucleus. So As we said, atoms and molecules can be identified by their electron distribution and their energy. And so we can take a beam of energy, electromagnetic energy like X-rays, and bombard a sample of matter. And so here is an electron detector counting the electrons that are being released by the influx of this electromagnetic energy. Again, you don't have to know the details of this, but you are going to have to be able to decode and interpret the results. So it measures the energies of electrons in a given shell. So PES helps us see graphically the energy of and the amount of electrons in a given shell. The position of each peak in the spectrum is equal to the energy required to remove an electron from the corresponding subshell. And the height of each peak is proportional to the number of electrons in that shell. This will make sense when we actually look at this. So here is an element. This is a PES of an element. We're going to find out that it's sodium, but what we're going to see in this is that, now be careful when you read this, because sometimes they read low to high and sometimes they're flipped and they read high to low. In this case, it's reading low to high. So this is saying it takes a relatively little amount of energy to release these electrons, and the height of those looks like maybe 1, because we know here this is going to be the core. This is going to be a 1s2. The highest energy is going to be the closest electrons to release. And so this is going to be 1s2. And then this is going to be 2s2. And then this is going to be 2p6. And you can see the P takes a little bit more energy. It's a little bit higher energy. So this is why we fill it from the lowest, right, the hardest to remove to the less. So 1s2, 2s2, 2p6, 3p. The height, it's not 2, it must be a 3p1. So this is indicative of an element that has 3 shells, a 1 shell, a 2 shell, and 1 electron in the 3rd shell. And that, if you look at a periodic table, represents sodium. So this is the sodium photoelectron spectra, the PES. Here is another PES spectrum, and this one, notice the energy is flipped, and this is often the way they're shown. They're often shown with the energy flipped because then that puts the core electrons on the left, and it's easier for us to read it kind of left to right. That's the way we tend to read things. So we'll read this as being, this is going to be the closest to the nucleus. Just remember, so here this is the closest to the nucleus. So you've got to pay attention to the scale. But here, this is the highest energy. So this is the core. This is the closest to the nucleus. This is 1s2, 2s2, 2p6, 3s2, that's full. 3p, how many? Well, this is 2, one more, 3, 3p3. So that corresponds to phosphorus. So every one of these is going to be like a thumbprint. Every electron is going to have its own unique PES that corresponds directly to its electron configuration, its unique electron configuration. So again, this is PES chart. This is 1s2, 2s2, 2p6, 3s2, 3p6, 4s looks like 1. So this looks like it would be potassium, if I'm not mistaken. So it's the first element that has a 4s1 electron. As I mentioned, pay attention to the direction. These PES things and these electronic configuration diagrams and representations help us predict and understand periodic trends. The trends in atomic properties that correspond to the electronic structure. So periodicity, periodic trends, repeating trends in atomic, physical, and chemical properties is explained by repeating electronic structure. So the periodic table shows patterns in both electronic structure and in properties, because it's that electronic structure that creates those properties. Remember, the organization of the periodic table is based on the recurring properties of elements, and it's explained by the recurring pattern of electron configurations and the presence of partially or completely filled shells and subshells. So these trends can be understood through the element's position, through the application of Coulomb's law, through the orbital shell model, and then the idea of the shielding caused by other electrons, and thus the effective nuclear charge of the positively charged nucleus. So these properties that we can predict and explain are the atomic and ionic radii, the size of atoms and ions, the ionization energy, the energy it takes to pluck electrons away from their orbital shells, away from the nucleus. It explains electron affinity, that is the energy released when electrons are captured by ions or atoms. And it also explains electronegativity, and that's the tendency within a bond for one atom to pull more strongly on the electrons than another atom. So we'll take these one by one, trends in atomic size. As I mentioned before, if you look at atomic radius, they start out big, and as you go down the same shell, adding more and more protons, the electrons get pulled closer and closer and closer until you get to a full p shell, 3p6 in this case. This is 2p6. And we bounce over here to 3. Now we start over with a bigger element. Why? Well, because we've added another shell. This is shell 1. Just has 2 electrons in it. This is shell 2, has 8. This is shell 3, has 8 plus these other ones in this D shell. But as you can see, it's an absolute regular pattern. They start out big and they get progressively smaller as we keep adding protons, which increases the effective nuclear charge, which pulls all the electrons, even though we're adding more and more together. And even though they have mutual repulsion between themselves, they're still being pulled tighter and tighter together because of increasing nuclear charge as we stay within the same shell. So the easiest way to remember this is that helium is the smallest, and francium is the biggest, and everything is going to go from biggest to smallest. So they're going to get smaller as we go left to right, but they're going to go bigger as we stack more and more concentric shells, Russian nest doll style, down the periodic table. So to sum it up, atom size generally increases as you move down a group. Why? Well, because when we go down a group, we are adding electrons to higher energy levels. And it's true that while the nuclear charge also increases, this higher energy level is further away from the previous energy level, and that increased distance has more of an effect than the increase of nuclear charge. So if we look at the, this is showing the electron shells. So this is shell 1. Okay, this is shell 1 and 2. This is shell 1, 2, and 3. Adding shell 4, adding shell 5, adding shell 6, adding shell 7. And as you can see, the more shells you get, the further you get from the pull of the nucleus, and the more interference these interior electrons provide, which is known as nuclear shielding. It's shielding these outer electrons from the full force of the nuclear charge. So as I said, the outermost orbital grows larger as we move down the periodic table, because as we move down, we are adding new shells every time. Now, as I said, we might expect the increased nuclear charge to overwhelm the additional electrons as it does when we go across the row and shrink the atom size, but not so. Not because the greater distance from the nucleus overcomes the increasing nuclear charge. So the distance creates less pull, greater distance creates less pull, increasing the protons creates more pull, a greater magnet, but the greater magnet is not as effective because it's trying to pull something that's relatively further away, so there will be less effective pull. Therefore, atomic size increases, the greater magnet of the protons is defeated by the less pull of being further away. And as I mentioned, atom size generally decreases as you move left to right because the principal energy levels remain the same, so there's no change in distance, but we add more and more protons, which adds to an increasing magnet, a stronger magnet. So it's the same energy level, same shielding, but a greater magnet, so there's a greater overall pull, pulls all the electrons close together. We call this increasing nuclear charge, and that's what accounts for the decreasing size of the atoms and ions as we go left to right. So if we look at this graphically, we can see when we go from hydrogen to helium, our size goes down, but then we add a new shell, and here we are at lithium. Okay, and then we go down, 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 and to what's this one going to be? Neon, and then we're going to bounce back up here to sodium. Then we're going to go down, 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 down. So basically, as we go left to right, when we get a new shell, we start big, but as we add increasing nuclear charge because of additional protons, we get small. And there's just almost no variation of this as we do this. All right, now let's look at trends in ionization energy. We know that the term ion means an atom has gained or lost an electron. And it takes energy to overcome the attraction of the nuclear charge and to pluck or to take an electron from a gaseous atom. So the energy to remove a mole of electrons from a mole of gaseous atoms is defined as ionization energy. So the atoms have to be in a gaseous form. We have to be talking about a mole of them, and Avogadro's number of them. And the energy to remove a mole of atoms from a mole of electrons from a mole of gaseous atoms is ionization energy. And as you would expect, the energy required to remove the first electron is called the first ionization energy. And that's going to be different from the energy required to remove the second electron. Because the second electron is going to be harder because why? Well, because now you've taken away one of the things that was counterbalancing the nuclear charge, the positive charge of the protons, and so the remaining electrons are going to be pulled harder and tighter than the others. And as you can see, the ionization energy is going to be the direct opposite of the chart we saw before. The ionization energy is going to get harder as the atoms get smaller. As they get closer to the nucleus, it's going to be harder to extract them. So you'll see this chart, if you remember, is the exact opposite of this chart. This chart, it goes down, right? We see this pattern of going down. The radius goes down, and ionization energy is going to go up, start over, up, 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 start over, up, 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 and so on. It's because as the size goes down, as we go left to right, then the energy it takes to extract electrons is going to proportionally go up. That makes sense. To remove a second electron requires more energy, and it's called the second ionization energy, and so forth. And when you start to put these numbers together, you're going to see a very definite pattern. You're going to see what's known as a jump. So if we look at the ionization energy, here's the ionization energy for sodium. To pull the first electron off, it takes this many kilojoules per mole. But to pull the second one off, look at this jump, it's almost 10 times as much. And then the jumps don't really get that high after that. So that tells us that this is a valence electron, and then now we are into the more core electrons. And this also tells us, just by looking at this, where this jump is that this must be a group 1 element. It must have a single valence electron. It's group 1. Over here, you have 2 relatively low numbers before you have this big jump. And that tells you that you have 2 valence electrons before you get to these inner core, harder to extract electrons. And so this must be a group 2 electron. A group 2 element. Here you have 3 relatively easy. Now again, they're not always going to be color-coded like this, but when you look at these number patterns, you should always be able to detect where's the big jump. From here to here, no, that's not too bad. Here to here, that's not too bad. Oh, well, here it is, giant number jump. And then not so giant after that. So here, this is like a 5 to 1 jump. After that, it's just like a 30% increase, whatever, 40% increase. But when you have these multiples, when you go a 10-fold increase or a 5-fold increase, another 5-fold increase, 4-fold increase, that jump is where you see the separation between your valence electrons and your core electrons. This tells you you've got 4 valence electrons. It is the oxygen group. Okay, 5 valence electrons, the phosphorus group, and so on. Okay, all the way down here to chlorine, where you have 7 valence electrons. So we can use the concept of ionization energy to predict ionic charges. If we see the jump between the easy to remove valence electrons and the hard to remove core electrons, then we know the number of valence electrons, we know what family it belongs to, we know what kind of ions. This is going to form a +1. It's going to get rid of this easy, and then it's going to be more stable. It's going to be harder. This is going to form a +2, +3. This will either be a +4 or a -4. This will be a minus, it's going to be a +3, -3. So it's got 5, needs 3 more. This is going to form a -2. It's got 6, it wants 2 more. This has got 7, it's going to form a -1. So you can predict the ionic charges just based on these ionization energy patterns. The first ionization generally decreases as you move down a group. Why? Because you're taking away electrons from shells that are further and further away. And it's easier to pick off those electrons the further they are from the nucleus. So just as the size of the atom increases as you go down a group, the electrons are further away, and therefore they're going to be easier to pick off. There's less shielding, less attraction, therefore lower ionization energy. Completely understandable from the point of Coulombic attraction. But the ionization generally increases as you move left to right. Why? Because the radius decreases, the charge increases, but the shielding stays the same. So it's harder to extract those electrons from the increased positive charge of the nucleus. So ionization energy is going to increase as we go up. It's the same as saying it decreases as we go down. And it goes just like the radius gets smaller towards helium, so ionization energy gets higher as we go to helium. It starts down here at francium and goes to helium. What about transit ionic size? Well, we know metallic elements have a low ionization energy because they love to form positive ions. Metals they're electron losers. They love to give them up. Nonmetals are electron winners. They love to gain them. And what effect does that have on ion size? Well, let's just look. Here is neutral lithium. But when it becomes a positively charged ion, it gives up its electron, its size goes from 152 to 60. So less than half of its original size. Whereas fluorine, here's the neutral atom, 72, when it gains electrons from, say, a lithium or something else, it nearly doubles in size. It goes to 136. You're going to see this pattern where cations are about half the size of their parent atom, and anions are about double the size of their parent atom. Anions are always larger because they've got extra electrons to distribute the nuclear attraction. And so it's going to allow those electrons to relax and to spread out further from the nucleus. The opposite is true of the the cations, they're going to have less electrons, and so the remaining ones are going to be pulled tighter to the nucleus. As the number of electron grows, so will the electron-electron repulsion. So not only are there more electrons dispersing the nuclear charge, now there's more electron-electron repulsion. So those two factors together increase the size of negatively charged ions. And then the effect is just the opposite for positively charged cations. They're always smaller because we have increased attraction, and oftentimes we've just lost an entire shell. In the group 1 and 2, they lose their entire shell and go back to a previous shell. So this is just, ionic radius is just like atomic radius with one important difference. These are going to decrease until you get to the negatively charged ions. And then these are going to start big again and then decrease. You'll see this graphically. Here we go. Here's graphically. They're going to decrease as they become positively charged, but then they're going to jump up again as they become negatively charged and then decrease again because of increasing nuclear charge. So it's just the same pattern as atomic radius with this reset when you get to the negatively charged ions. About trends in electronegativity. What is electronegativity? The tendency of a bonded atom to attract electrons to itself. Think of it this way. In every bond, atoms play a tug-of-war to pull the electrons to themselves. And the more electronegative an atom is, the more it wins the tug-of-war, the more it pulls the electrons to its side. So we've calculated electronegativities and we express them in arbitrary units known as the Pauling electronegative scale. So these are just, they have no units, it's just kind of a reference. So basically everything is made in reference to fluorine, which happens to be the most electronegative, and then everything else is kind of how close to fluorine is its pull. So the key thing to notice is that cesium has the least electronegativity, fluorine has the most electronegativity. Notice the noble gases are not represented because they don't have any electronegativity. They're completely happy. They're not trying to grab or pull electrons. So they don't have an electronegativity number. So it goes from francium or cesium at 0.7 all the way to fluorine. And as you can see, as the closer you get to fluorine, things like oxygen and chlorine, and nitrogen, and sulfur are going to have much higher electronegativities than these other metals. So basically the non-metals tend to be much more electronegative than the metals. That's a good rule of thumb. We pass over the noble gases because they don't form a lot of compounds. It goes down a group as you'd expect because they're getting bigger and bigger, but it increases left to right as you would expect because of increasing nuclear charge and other things. But the key thing to remember, fluorine is the most electronegative. Fluorine is like this bigger, stronger girl, and they're pulling electrons. This girl will always be able to pull that rope, the electrons closer to herself. Fluorine's electronegativity is so strong when it's bonded to any other element, it either pulls the shared electrons to itself or it completely steals them to form a negative ion. So that's all you have to remember. You'll always get electronegativity right if you remember that fluorine is the most electronegative. What's the practical payoff? Well, electronegativity allows us to predict what kinds of bonds will form between different atoms. So if there is a if there's a big electronegativity difference, the stronger atom is going to pull the electrons much closer to itself and create the possibility of polar bonds and polar molecules. If it's super strong, then the strong one actually pulls the electrons completely to itself and creates ionic bonding. So electronegativity difference is what accounts for neutral covalent bonds, polar covalent bonds, and ionic bonds that are basically stolen electrons. So putting it all together, here are all the things we care about. Electronegativity increases as we go to the right, decreases as we go down. Ionization energy, same thing, increases as we go to the right, decreases as we go down. Atomic radius decreases as we go to the right, increased nuclear charge increases as we go down. Nuclear charge increases as we go to the right. Yeah, sorry about that. Nuclear charge increases in both directions. Every time we add a proton, we increase nuclear charge. And finally, shielding is constant as we go across a group, but shielding increases as we go down a group. So here is everything together. And if you can remember these general trends, you can get a lot of answers right on the AP exam. All right, valence electrons and ionic compounds. The likelihood the element will form chemical bonds is determined by the valence electrons. And all the elements in the same group will tend to form analogous compounds because they have similar, or the very same valence electrons. So they'll form similar ionic compounds. They'll have similar ionic charges. And these are controlled by the location on the periodic table because that tells us the valence electrons. So as we can see here, all the group 1s have a single valence electron in their outermost shell. These have 2, these have 3, and so on. So key concepts: the mole, molar mass, average atomic mass, which is the weighted average of the isotopes, empirical formula, which is the lowest ratio, we can compare that to molecular formula, electronic configuration, using our Aufbau and our Pauli exclusion and our Hund's pairing rules, the difference between core and valence electrons, Coulomb's law, force is directly proportional to the product of the charges divided by the square of the distance, PES spectra that tell us the location of the various orbital subshells, periodic trends, how they're affected by those electronic patterns, the difference between nuclear charge and shielding, how atomic and ionic radii decrease when we go left to right, how ionization increases as we go left to right, how electron affinity increases left to right, how electronegativity increases as we go left to right, the difference between valence electrons, or how valence electrons create analogous compounds. That is it. Thank you for your time.